Welcome back to Math Heads 101. Um, Today I'm going to show you how to get the area under the curve, also known as an integral, indefinite integral. Okay? So, first we need to know the area of a rectangle. So the area of a rectangle is the height times the base. So area is equal to HB. Okay? Pretty simple. Because you're taking all the bases and multiplying them by all the heights. So now let's figure out the area under a curve. So let's pick a nice curve. Let's do, I don't know. Okay, I'll teach you the abstract first. Here's our curve. We want the area between the curve and the x-axis bounded by these 2 points. This is the area we're looking for, the area of that. How do we get that? By the way, this is f of x. That's your function, and this is the x-axis. This is the y-axis, or the x-axis. We'll name this A and B. Okay. It's a little bit of glare. Okay. So what we're going to do is we know the area of a rectangle, so we're going to use a bunch of rectangles. So we have a rectangle here, and a rectangle here, and a rectangle. I'm going to erase this. Okay. So we have all these rectangles inside. So you might say to me, hey, that's not the area. You're forgetting about this part, and this part, and this part. So how do we do that? We're going to make the rectangles infinitely thin. So they're a bunch of lines, but we're going to give them a little bit of width. So we said that D means really small. So they're going to have width dx. So just a little bit of a change in x. And then the height, that's just the value of the function. So f of x. Okay, so that's going to be the area of one of those rectangles. The base, this is the base, times the height. And this is the height. And my handwriting is awful. But we didn't want the area under one of them, we wanted the area under all of them. So the operator that lets you take infinite amount of infinitely small things is called an integral. So it looks like this, it's just that nice little shape, a big S. S stands for sum, by the way, that's why it looks like an S, because you're summing up all these little things. And which ones are you summing? You're summing them, all of them, from A to B. Bang. So that's how you do it. And that turns out to be equal to, alright, we're going to say that the derivative of big F of x is equal to little f of x. Okay, so now this is equal to big F of B minus big F of A from the fundamental theorem of calculus. But that part, focus on later. Focus on this part now. Infinite amounts of small rectangles. And don't think about why the derivative is involved. So let's do a problem. Let's do the area under... let's do something we can figure out the answer of. So we know that a circle has pi r squared area. So half a circle is pi r squared over 2. So we're going to want so let's graph. So the equation of a circle, so you know that for a circle, y squared plus x squared equals the radius squared. So now we're going to solve that for y. So we're going to say y equals plus or minus the square root of r squared minus x squared. Right? But, so that's going to look like that. Where this is minus r and this is r. But we're going to only worry about the positive one. Because we want half a circle. So the answer should be pi r squared over 2. Let's see if we get that. So we have the integral from minus r to r of the square root of r squared minus x squared dx. So how do we evaluate that? Probably gonna need some trig substitution somewhere. Let me try. By the way, this is a bad problem to start with. I don't know why I gave it to you. Let r squared equal, what could r squared equal? Sine, no, let r squared equal cosine theta. Right? For some theta. Okay. So the r squared I don't know. Bye.